I've been working on this game theory ontology for a while now. I'm going to say some stuff that will be somewhat controversial to this group, and I'm looking forward to see what you have to say. There are definitions coming around too. You don't need to look at these while I talk because I'm going to talk really fast, but if you have questions that you have about them afterwards, you can send me an email if you find problems with them, which I'm sure you will, but this will explain some of the motivations. So I want to lay out some basic components of game theory. I want to explain an ontological approach to game theory, and I want to describe a potential application that I see for this. So decision theory falls into a group of theories associated with rational choice theory. So decision theory studies rational choices in terms of preferred outcomes and beliefs about the likelihood of these outcomes, and game theory is interested in that when those outcomes are determined by the interactions of deliberating agents. I thought of all of these, game theory seemed like a good place to start. Social choice theory, which is about those outcomes and the likelihoods over groups of interacting agents, seemed like it would be easy to get at if we could do game theory right. So here is a decision matrix for the game rock, paper, scissors. All of you know how to play this. Right? We know what the rules of rock, paper, scissors are. What you see here are some of our basic elements. So these are the choices that are open to one player, the choices that are open to the other player, and then these are our potential outcomes. These are possibilities. And in each one of these cells, there's a possibility along with a set, and these sets are the potential values relative to each player of that outcome. So I set the bar for trying to capture this kind of information in games. Here also is a decision tree showing probabilities for a coin toss. We can see different probabilities for different outcomes. The probability of throwing a heads twice is 25. So we would want to be able to develop a system that could generate something like this too. And there are plenty of game theory programs that do just this. So I was sort of thinking there's probably a lot of information about games that's developed like this. What would that data look like, and how could we develop an ontology that would allow us to tag those kinds of entities? This is a word map that I generated off the SEP article on game theory, and you can see some of the major elements that you might want to capture jump out at you. Game, of course, is a big one, but so is utility, information about games, notions of rationality, agents, sets, players, outcomes, possibilities, solutions. All right. A major distinction that is not as often made in the literature is between what I'm calling game models, which are information that is about the players' knowledge states, actions, preferences, and other components of games. And games themselves, which are real events that take place in the real world and involve people playing games. So we could have real games that are satisfactions of certain descriptions of them multiple times. And we could also just be interested in the formal quality of these abstractions independently of the real events. So making this distinction seems like an incredibly important one that's not often made in some of the literature. I also have agents here as a defined class of person or organization that has some capacity for intentional action. You could weaken this if you wanted to also add computer agents, I suppose, or you could treat computer agents separately. I haven't included them here. But players are going to be roles that those agents take on or take off within the context of a game. Prisoner's dilemma, most of you are familiar with this. I'm not going to read it to you. We have a situation here that describes two players and their potential outcomes if they're both arrested and they're deciding whether or not to defect or cooperate. Most of us are familiar with this, so I'm not going to read it through. This is a decision matrix that shows us the possibilities, but it's describing a real situation that's occurring. And these different elements either describe elements of the real event that are occurring or are predictions that are occurring in real time. And this decision matrix is a game model. That is a game, or at least it's a picture of that's supposed to represent here a real event happening in the world. One basic question, how should we treat probability in Buffo? This is a problem that lots of us have thought about, and there are different treatments of probability in semantic web technologies. I don't think basic formal ontology has a great one. You might think that we should go the disposition route. So Karl Popper held this view, the propensity interpretation, that probabilities are dispositions of an object that are realized in certain effects. I want to bring to your attention two problems I see with this. The first is identifying the bearer of the disposition. Maybe it seems relatively intuitive to say that the coin that I toss in the air has a disposition to fall heads up or tails up 50-50. But when we start talking about larger events, I don't know how to individuate the dispositions such that we say there's one disposition or two dispositions or 50 dispositions. And I don't know how to carve up the granularity. Dispositions don't seem amenable to that, especially when we're talking about, say, the probability of Trump winning the election, right? Is that a disposition that adheres in Trump, or lots of dispositions that all engage with one another? It's difficult to model that. The other one is Humphrey's paradox, which is a long-standing problem for Popper's view. This follows Bayes' theorem, which says that we can calculate inverse probabilities using Bayes' theorem. So if we know the probability of A given B, we can also compute the probability of B given A. Now, dispositions, unfortunately, can't be inverted this way, or at least that's my interpretation. So I'll slow down and we can spend some time on this slide. I'll go ahead and read it with you. The first premise here says, suppose we know the probability that a train will arrive on time given its start time. In other words, we know the probability of A given B. If the propensity theory is correct, then we say the train has a disposition that is realized in on-time arrival if it leaves at the given start time. From Bayes' theorem, we can calculate the inverse probability of the train starting at a given time given on-time arrival. But it makes no sense to say that given its on-time arrival, the train has a disposition to have had arrived a few hours earlier. This isn't how dispositions work. Dispositions are realized in future events, not past ones. And so therefore this propensity theory is incorrect. Dispositions seem to have a directionality sort of like causation, where they aim forward. But probabilities seem to aim both forward and backward at the same time. Future events can tell us information about the probabilities of past events. So I don't think that this account's going to work. I think we need something else. So I have taken probabilities and pushed them up into information land. It's not a great solution, but that's where they're living. So speculative information content entities are information content entities that are about some occurrent where that occurrent is unknown to the creator of the descriptive information content entities. These are serving my role as possibilities. Then there are two subkinds of these, predictive and retrodictive. So predictive information content entities are going to be the speculative information content entities that are created by an agent at a temporal interval 1 and that predict an occurrent that occurs at a later temporal interval. Retrodiction is where you're making a guess about an event that's already occurred. So if Brian comes in the room and he's crying, then I make a guess about what caused him to cry in the past. That's a retrodictive information content entity. Rules, strategies, and game types. I have treatments of strategies and game types, but a lot of them are just included in defined classes because I think that the elements that I need for them already end up being accounted for by these possibility treatments. So for instance, you might treat some kinds of rules as sequences of, or as given to you by the available possibilities. Similarly, strategies might consist of sequences of possibilities along with their outcomes. And game types will be given to you by other features that are available in the game. So a sequential game, for instance, will be a game in which the players end up making a move every other turn. So we can create a lot of these just with defined classes. Outcomes are going to be occurrence that are the output of an action of a player in the context of a game. Likelihoods are going to be the values that probabilities get assigned. I'm going to move through this quickly because you already have this on your handout. So here's a basic picture. There's a predictive information content entity that gets assigned a probability value that predicts some later outcome, where that outcome is a real event, a real occurrent. So here is my treatment of tossing a coin. So here, there's going to be, in the future, at time t plus 1, an outcome of this coin toss. But right now, I have these predictions that represent the coin landing heads up, that represent the coin landing heads tails. These engage in a possibility space function that assigns them probability values that have text values. Make sense? Okay, proceed forward. Now, preferences are also extremely important. I removed a bunch of slides here for time, but preferences can be dispositions to prefer. They can also be revealed in actions. So we want to distinguish between these two ways of talking about preferences. And preferences are not values. I can have a preference to go and eat at Rose's Pizza that I can think of as first, second, third, or that I can think of as 99% on a 100% scale. They would never get that high. Or that I can think of as best or worst. So I can measure them in different ways. So preferences are antecedents to the different values they might take on. So I have classes of preference profiles that are dispositions that inhere in an agent and are realized in acts of preferring. And I have acts of preferring that are cognitive acts that both affect and realize one's preference profile. The idea is that when you prefer something actively, you're both reaffirming your disposition, but you're also realizing that disposition. There's a sort of dynamic quality that they have. So let me go through an example. Jones and Smith want to eat a quick lunch together. There are 3 restaurants, 1, 2, and 3. For each, there's a probability associated with getting timely service. For each, Jones and Smith weigh their merits differently. For both, Jones and Smith want the restaurant that is likely to give them the best meal in a timely fashion. Now, they want to eat together. They want to make each other happy. This isn't the best game theory example because they're not competing off one another. But they both have their individual preferences. Now, Jones, I think, simulates each possibility. This produces sentiments for each possibility. He imagines eating at these different restaurants and what that experience would be like. He judges that, and these are all parts of an act of preferring that realizes his general disposition. Now, for each of these simulations, there are sentiments that are created for each simulation that he then measures. And on this act of measurement, there's a value that gets spit out on the other side. These aren't classes here. These are actually RDF statements, but I needed the space to include them. So sentiment 1 has ratio value 5, sentiment 2 has ratio value 3, etc. Take these, move them over here. And now what we can say is these values will be an input in a utility function where they get times by the probability of getting on-time service. And that gives you your expected utilities for each possibility that Jones has simulated. Imagine we do this also for Smith now. We can put these in a decision matrix. We know that they were only interested in eating together, so we can exclude other possibilities. We can add those together, and we can see clearly where they should end up eating. So there's a bit of the OWL file. So some benefits: make heterogeneous data concerning games interoperable, unify game theory models with real intelligence. This is something that I don't think has adequately been done. And a lot of this work that I was interested in really stemmed from work by Bruce Bueno de Mesquita, who has a wonderful TED Talk where he talks about some of his work using game theory to predict geopolitical events. So apparently he's been able to predict with 90% accuracy whether or not some player will end up winning the presidency of Yemen, or whether or not some treaty will be signed, or in 2009, whether or not Ahmadinejad would end up getting a bomb in the next 2 years. He adds categories to traditional game theory, including who influences who, what interactions they have, the stakeholders, influencers, the credit, the salience of the issue, and how flexible the people making the decisions can be. But all of those would be easy to add to the basic schema I've set up. So something I'm interested in is a possible intelligence application of this, which is to create an RDF store of game properties to serve as a library of properties like Nash equilibria. Now, Nash equilibria are really important in game theory. They are solution concepts of non-cooperative games involving 2 or more players in which each player is assumed to know the equilibrium strategies of the other players and no player has anything to gain by changing his own strategy. In this case, the Nash equilibria is this possibility because each player would potentially end up doing much worse by switching their strategies and choosing a different choice. Now, the Nash equilibrias are really important and they serve a number of different purposes. First of all, if you advise any strategy other than the Nash to players in a game, that means for some players that advice would be really bad. Right? They could end up losing heavily if you advise them anything but the Nash. Also, when the goal is prediction, we're trying to predict if we iterated this prisoner's dilemma over and over again and had them play. The Nash serves as a stable point. in a process of dynamic adjusting, where they're adjusting back and forth what their choices should be, and where players are searching for the best possible strategies. So if we're trying to predict what's going to happen in the long run, we need to look at features like this. On the other hand, the Nash is really hard to compute. When you have lots of variables, it becomes a computationally difficult problem, and it's hard for computers to calculate efficiently. So here's my idea. If we compute the Nash equilibria for lots of different game configurations that have different values, we can do that on our own time, slowly. Right? We can let that run. But use that to create a library of Nash equilibria tagged to game configurations. Then, as you have real-time data coming in, you can use an RDF triple store to tag the Nash rather than calculating it on the fly. So this would give you a way of identifying predictions in real-time data when the games are relatively complicated, but not having to do that quickly. So if we had a question like whether or not our good friends in North Korea are going to get a bomb, we could model that using some game model and then draw from an RDF store the Nash equilibria to tag the possibility that we expect them to use as a stable point. Anyway, I think that's a potentially interesting application of this work. So there we go. Questions? Yeah.
So I have a question about your definition of speculative information content.
Yeah.
I think there's a bit of an ambiguity in it, and I want to know how you intend it to be taken. So you define a speculative information content entity as an information content entity that is about some current, where that occurrence is unknown to the creator of the descriptive information content entity, and the notion of unknown there I think is both ambiguous. So I don't know if you mean the person who has or has created this information content entity does not know whether the occurrence exists or whether he knows that the occurrence doesn't exist.
Good. So that is ambiguous. And originally, when I was tackling this problem, there's a distinction that's often made between objective and subjective possibilities, where the objective possibilities are sort of relative to a total information state. The subjective possibilities are relative to the information state of the individual agent who's acting, even though we might know better. And I foresee taking this distinction and blowing it out a little further so that we can end up making that subjective-objective distinction. But I haven't done that yet, because I've only recently decided to reconfigure how I thought about this. I do think it's going to be the case that we know the agent's going to know what this information content entity is. They won't know whether or not it obtains of the occurrent.
So it seems to me like if this is trying to capture, this is supposed to be information about possibilities. In many cases, possibilities, I know that they don't actually apply. They don't actually occur. Right? I know that. I know that it's possible you have a beard, but I know that you don't have a beard. So it does seem like I know whether or not it holds a beard.
Is the idea that I'm using knowledge in a strange sense?
So on the one hand, I think I understand your motivation for taking this sort of approach.
Yeah.
Possibilities are things that may or may not occur, things that you can still sort of talk about, whether or not they actually happen. I think that's, if I understand you correctly, I think that's the kind of angle you're coming from. It seems to me a bit off to talk about it as either not knowing whether it holds is the thing, that's the possibility. In many cases, I think, if I understand you correctly, I do know that it doesn't hold of this thing, and that's why I think it's a possibility, right? I think it's possible for you to have a beard, partially because I know you don't actually have a beard.
So I'm only interested in the sense of possibility as it gets discussed in game theory, where it's sort of forward-looking and agential. So I'm not interested in the possibility that I was born a goldfish or something like that, or that I'm a round circle or a square circle. So if there's, I mean, I agree, there's probably ways in which I could change up the definition a little bit. But I hope that it's implicit that I'm not interested in this wider sense.
Okay.
Okay. I didn't quite do justice to your question.
I'm not terribly familiar with the Nash equilibrium. Is there much work done that might take into account things like preferences and strategies or what have you? Because it seems like the Nash equilibrium maintains that everybody has to have the same type of preference for the same type of outcome, and that just seems like it's not the case.
So these are going to be expected utilities, right, that are generated, and the Nash is going to be computed over them. So we could model these differently using different preferences or different scales, but the Nash is going to be a property of the ways in which these are configured together. So I don't know if I'm doing justice to your question or not.
So what about when multiple actors have different preferences?
Yeah, that could very well be the case here. I mean, maybe Smith and Jones have really different preferences.
Smith wants to go to prisoners.
Yeah, sure.
Or you can watch the Beautiful Mind, the movie, the generation.
Yeah, it's not required that they have the same preferences as Nash talks about.
Yeah.
Okay.
Good. Ben?
I thought you were running, John.
We have limited time here.
Hey, this is probably quick. Your occurs at relation is, how do you define that?
Please don't tell me I did it wrong.
No, I was just curious. So is this like is this a subclass of occurs in at?
No.
It's just occurs at, so is it like a primitive? How do you define that? Say,
Where are
I
you-
don't know. with
where are you
respect to
looking at?
buffer. In your predictive information content entity, you have interval 1 occurs before, and before that you have predicts an occurrence that occurs at a temporal interval. I'm just curious how you define the occurs at relation. Where does that go?
I was just thinking it occurs during. So.
Yeah. So I was thinking occurs in. It occurs in something, and then it's like time indexed. So A occurs in B at T. I was thinking you might want to define occurs in with respect to that. I don't think so. I think there are other ways you might do it, but I was just curious if you had an idea.
No, but maybe we can talk about that afterwards, because
Sounds good.
yeah, if you wanted to push on that, that could be beneficial.
I mean, I don't think it's an objection. Just
Ben?
But it seems like preferences are too narrow in being the result of cognitive actions, right? Because you can have states as the decision makers, right? Or it could be modeling the preferences of like a species, and if we're doing evolutionary game theory, it seems like the preference profile is not a result of cognitive acts of preferring, but of just whatever they're sort of like whatever turns out to be fitness enhancing and things like this.
Great question. So in the slides that I took out, I had a slide about myself going to lunch and how I would prefer, and I think of that in terms of simulation. I could describe to you why I prefer those things by citing facts about how I'd simulated going there. In the second case, I had a picture of my cat and what my cat prefers, whether he prefers one cat food to another. We can't ask my cat. My cat might not simulate his preferences about cat food, but his preferences are revealed in his disposition to eat some foods over others. And so you could model it either on the basis of actions or on citing the disposition he has. In the case of a computer agent like Deep Blue, who famously beat Garry Kasparov, I think the programming that the computer has is, in a sense, a preference profile. It has all of its preferences oriented in its programming, and they are exercised in the actions that it takes and revealed there. And I think that's a permissible use of the term preference.